this video, we'll take a look at sequences and see how they're related to functions. We'll define alternating and recursive sequences and introduce summation notation to find the sum of the terms of a sequence. PreCalculus Online starts now. In section 12.1, we look at sequences. So the first question is, what is a sequence? Well, a sequence is a function whose domain is the set of positive integers. It's a function whose domain is the set of positive integers. So let's take a look and see the differences between functions that we've studied up to now and then sequences, which are just functions with positive integers as the domain. So for example, if I take this f of x is equal to 2x plus 1, and I were to ask you to graph that, you would probably graph something like this. It's a line, and it goes through the point 0, 1, and then it goes through the point here, that would be 1, 3, and then 2, 5, etc. Now, whenever we talk about a sequence, notice that we sort of denote it by an A with a subscript. That subscript is the index number, so this means that the nth term of sequence denoted by the A. So that's sort of similar to function notation where we had f of x, and the x represented what number was being evaluated in the function. And then similar to a function, we have an expression that defines the sequence, what terms are going to come out of the sequence. Well, let's look at the graph now. So for starters, we're only allowed to use positive integers for the n. So this is sort of the n-axis, as if this were the x-axis. And this would, of course, start at 1. And the value for 1 would be 2 times 1 plus 1, which is 3. So we would have this point here. And so this point represents the a sub 1 term being equal to 3. Similarly, I could do a sub 2, which is the second term. So it would be 2 times 2 plus 1 is equal to 5. So for n is equal to 2, we get a term that is 5. And then this would continue. But notice the big difference here. On the left, we have a function, and that function produces the entire line. On the right, we have a sequence, and the sequence only produces these little discrete points. We're not going to connect these points. The points themselves represent the sequence of values. If you sort of look at it on the y-axis, those are the sequence terms here, 3, 5, 7, 9, etc. So that's the difference. You have a function whose domain is only the positive integers, and then that's a sequence. Example number 2. Write down the first 6 terms of the sequence defined by a sub n is equal to n plus 1 over n. So a sub 1 means that the value of n is 1. So every place where there is an n, we're going to place a 1. So this would be 1 plus 1 divided by 1. And the red here indicates where the 1s have been placed. So that works out to be 2. A sub 2 is equal to 2 plus 1 over 2. And you work this out to be 3 over 2. A sub 3 is going to be 3 plus 1 over 3. So we're just replacing the n's with their appropriate number here. Oops. So that's going to be 4 over 3. A sub 4 is going to be equal to 4 plus 1 over 4. That would be equal to 5/4. A sub 5 is the fifth term. That's equal to 5 plus 1 over 5. That's equal to 6/5. And A sub 6 is equal to 6 plus 1 over 6, which is equal to 7/6. So the first 6 terms of this sequence are 2, 3/2, 4/3, 5/4, 6/5, 7/6, and of course the sequence goes on forever. One special type of sequence is called an alternating sequence. An alternating sequence is a sequence that alternates between positive and negative terms. So you have one positive term followed by a negative term, followed by a positive term, followed by a negative term, or it could start with a negative term and then alternate. It doesn't matter. But every term switches signs. And the way that they accomplish writing down the alternating part is by using -1 to some power. The power could be n plus 1, it could be n, it could be n minus 1, it could be various other things. But you just have to check to make sure it alternates back and forth. If you have -1 to a power like n plus 1, then that power is going to be odd in one situation and then even in the next, and it's just going to alternate from odd to even. That's what produces the -1 multiplier, or produces +1 as a multiplier, giving us the alternating part. Example 3. Write down the first 6 terms of this sequence. B sub n is equal to -1 to the n plus 1 power times n squared. So the first thing to note here is that the n squared part is just going to give me the square numbers. So b sub 1 will be partly 1, b sub 2 will be partly 4, b sub 3 is going to be partly 9, b4 is going to be 16, b5 is going to be 25, and b6 is going to be 36. Now the question is, it alternates, but what does it start with, a positive or a negative? So let's just work that out. So -1 for the first term here, b1, is going to be -1 to the 1 plus 1. That would be -1 squared, which is +1. So the first term is positive, and then -1 to the 2 plus 1 is -1 cubed, so that would be -1. Well, that's negative, so it just alternates right here. So all of the even numbers, even indexed numbers, are negative, and all the odd index numbers are positive. So the sequence is 1, -4, 9, -16, 25, -36. Dot, dot, dot. Example 4. Determine an expression for the sequence that gives the following pattern. Alright, so our first one is 1, then 1/2, 1/3, 1/4, 1/5. So basically what you're trying to fit is a sequence, a sub n, that matches the following data. The n's are going to be 1, 2, 3, 4, and 5, and the sequence terms are going to be 1, 1/2, 1/3, 1/4, 1/5, and you need to come up with the expression for n that would match this. So I think this one is sort of straightforward. We say that a sub n, the sequence, is equal to the sequences of 1 over n, because you're just taking the reciprocal of the index number on the left. So that would be 1 over n. Part B would be -8, -3, 2, 7, 12, 17. So if I try to do this trick again here, let's call this B sub n, we would have 1, 2, 3, 4, 5, 6 numbers, and they are -8, -3, 2, 7, 12, 17. So I don't immediately see a pattern based on the index like I did in the previous one. So one strategy that you can try is called taking differences. So if you just take the difference for each of these and see what they are, so -3 minus -8 is +5. 2 minus 3, -3 is +5. 7 minus 2 is 5. 12 minus 7 is 5. This is also a 5. So we have a common difference. And whenever you have a common difference, then it means it acts sort of like a linear function. So really what I'm looking at here is that with each additional term, I'm gaining 5. So that sort of acts like a slope. So it's going to be 5n. Remember that we use n here instead of x's. So it's going to be like 5n. The question is, where does it start? So just like we would have a y-intercept that would correspond to x equals 0, I like to pretend that there is a 0th term. Now the 0th term doesn't really exist, but it sure is helpful if we pretend that it exists and then figure out what number that would be. So if I just sort of backtrack by 5 here, what number would the 0th term have been if it actually existed? Well, it would be -13. And so there we go. So our sequence, B sub n, is equal to 5n minus 13. Next, we look at recursively defined sequences. So a recursively defined sequence is one that gives you a little bit of information to start with. That little bit of information is called the seed. And then it gives you a formula for determining the other terms. But the formula that produces the next terms piggybacks on the previous terms in some way. And so you have to know what the previous terms were to produce the next term. So that's the recursion part. You go back to figure out what that was to produce the next term. Example 5. Write down the first 6 terms of the recursively defined sequence. S sub 1 is equal to 1, and S sub n is equal to n times S sub n minus 1 for n greater than or equal to 2. So our seed is S sub 1 is equal to 1, and then this is the recursion. So what you see here in the recursion is that in order to produce S sub n, you actually need to know what the previous term was, which is S sub n minus 1. So we can write down some of these terms here. So S sub 1 is equal to 1. S sub 2 is going to be equal to, using the formula, 2 times S sub 2 minus 1, which is the same thing as 2 times S sub 1. And then S sub 1 is 1, so this is 2 times 1, which is equal to 2. Then S sub 3 is equal to n, which is 3, times S sub n minus 1, so that's 3 minus 1. So that tells us to use 3 times S sub 2. So the previous term to S sub 3 is S sub 2. But 3 times S sub 2, and I'm going to use this version here for a second so that you can see a pattern. This is 3 times 2 times 1, which is 6. Next we get S sub 4, which would be 4 times S sub 4 minus 1, which is 4 times S sub 3. And so this would be 4 times the previous multiplication. 3 times 2 times 1. 4 times 3 times 2 times 1 is 24. Hopefully you're seeing the pattern here. Let's continue on. S sub 5 would be 5 times S sub 5 minus 1, which would be 5 times S sub 4, but S sub 4 was 4 times 3 times 2 times 1, which is 120. And the last one, S sub 6, is equal to 6 times S sub 6 minus 1, which would be 6 times S sub 5, which is 6 times 5 times 4 times 3 times 2 times 1, which is 720. Now you may have seen numbers like this before. These numbers are called factorials. So the above is the definition of factorials. And the symbol for factorial is you take the number and you put an exclamation mark beside it. So that is read as n factorial, and that is equal to n times n minus 1 times n minus 2 times dot dot dot, and you multiply the integer n times the number less than it, n minus 1, times the number less than that, n minus 2, and you go all the way back down until you get to times 2 times 1. And those are the factorial numbers. So for example, this last one, 720 S sub 6, is the equivalent of 6 factorial. Now, one thing to note that we're going to need a little bit later on in this course is what is 0 factorial defined to be, and that is actually defined to be 1 for reasons that we will talk about when we get to that section. Example 6. Write down the first 6 terms of the recursively defined sequence. T sub 1 is equal to 1, T sub 2 is equal to 2, T sub n is equal to 2 times T sub n minus 1 minus T sub n minus 2. So in this problem we have 2 seeds, and then our recursion goes back to the first previous number and then the second previous number. So we're going back 1 term and then 2 terms. So let's write down the first 2 terms here. So T1 is 1, T2 is 2. Let's compute T3, and that would be 2 times T sub 2 minus T sub 1. That is equal to 2 times 2 minus 1. 2 times 2 is 4, minus 1 is 3. So T sub 3 is equal to 3. Let's compute T sub 4. So this would be 2 times T sub 3, the previous term from T sub 4 is T3, minus the second previous term from T4, which would be T2. This is 2 times 3 minus 2. Which would be 6 minus 2, which is 4. So T sub 4 is 4. T sub 5 would be 2 times T sub 4 minus T sub 3, which is 2 times 4 minus 3, which is 5. So there's a pattern here. And then lastly, T sub 6 is equal to 2 times T sub 5 minus T sub 4, which is equal to 2 times T sub 5 was 5, T sub 4 was 4, so this is equal to 6. So the first 6 terms of this sequence are 1, 2, 3, 4, 5, 6. And you probably guessed it by now, but yes, it can be shown using methods not available in this class, but in a discrete math class that if you're a computer science major, you will have to take. And this is a really fun problem in that class. that the sequence t sub n is actually just the sequence of integers. Whenever you work it out and you remove the recursion part, this has a general form, or what they call a closed form. It's actually just the integers themselves. Our next topic is summation notation. So suppose you're given a sequence a sub n, and you want the sum of the first n terms of the sequence. So that would be a sub 1, and we're adding, so it would be plus a sub 2 plus a sub 3 plus dot dot dot. The last term we'll use here is a sub n, that's the first n terms of the sequence. And then we have summation notation, also called sigma notation. The Greek letter sigma, it's the capital one, looks like this. And this would be, under the sigma would be k equals 1, and that's your index. And then the top would be an n, and then you would say a sub k here. So these things are the index variable, k, and it could be other letters, right? So it doesn't matter what the index variable is. This is representing an idea and a position holder. And then at the bottom you have the start number, and at the top you have the ending number. And then we have the expression to use. So this says take the index numbers for a sub k, start with 1, and add them up going all the way through a sub n. So let's see an example. Example 7. Write out the summation. The sum from k equals 1 to 4 of 3k plus 1. So let's write that out. So the sum as k goes from 1 to 4 of 3k plus 1. And all we do is we're going to plug in k equals 1 into the expression. So that's going to be 3 times 1, that 1 comes from the k, plus 1, plus, then we're going to plug in k equals 2. So it's going to be 3 times 2 plus 1, plus, then we're going to plug in 3. So k is going to be equal to 3, so we get 3 times 3 plus 1, plus, and lastly, k is equal to 4 because that's our upper index, so it's 3 times 4 plus 1. So that's how the terms of the sum, the add-ins, are going to be computed. And then we just work all this out. So 3 times 1 plus 1 is 4, the next one is 7, the next one is 10, the next one is 13, and you add that up and you get 34. Next, example 8, write out the summation, the sum from k equals 5 to 10 of the cosine of k times pi, and then find the sum. So the sum as k goes from 5 to 10 of the cosine of k times pi, that would be equal to, first k is equal to 5, and by the way, me writing this k is equal to 5, that's completely optional. That's just so that you can see what I'm doing. Normally people don't do that. But this would be the cosine of 5 pi plus k is equal to 6, gives me cosine of 6 pi, plus the next one, cosine of 7 pi, plus the cosine of 8 pi, plus the cosine of 9 pi, plus the cosine of 10 pi. And the upper index was 10, so that's where we stop. And now we work this out. What is the cosine of 5 pi? Well, 5 pi would be in this position here, so that's going to be negative 1. And then the cosine of 6 pi would be back in the original 0 spot, so that's plus 1. 7 pi is back over here on the left side, so it's negative 1, then plus positive 1, then minus 1, then plus 1. So we get negative 1s and positive 1s in equal measure, and so that's equal to 0. They all cancel out. Next, what are the properties of summations? So here, again, the sigma represents summations, and so we have some techniques that we can use to help us with these. The first one is the sum as k goes from 1 to n of c times a sub k. So a sub k represents the terms of a sequence, but c is going to be a real number. You can simplify that by pulling the c out to the front, right there. And you get c times, so this is times right here, the sum k equals 1 to n of a sub k. That's nothing more than the distributive sequence, distributive property rather. Because you would have, for example, c times a sub 1, c times a sub 2, dot, 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 and then you can just factor out the c. Like that. And so then this part here becomes the summation of just the a sub k's, whereas this part up here was the summation of c times a sub k's. The second property says that the sum from k equals 1 to n of a sub k plus b sub k is equal to the sum of the a sub k terms plus the sum of the b sub k terms. So in other words, you can break up the sum by representing them as two different sequences and splitting them off. Same thing here. It's if they're subtracted, you can break them off. And then the last one is sort of interesting. It says that the sum of k equals j plus 1 to n of a sequence a sub k is equal to the sum as k goes from 1 to n of a sub k minus the sum as k goes from 1 to j of a sub k for all j that is between 0 and 1, 0 and n. So essentially what's happening here is, let's look at this first piece right here. The sum as k goes from 1 to n, that is essentially taking the sequence and starting at 1. Let me draw it like this. Taking the sequence, starting at 1, and then going out to n, and adding all of them together. So here are all the terms of the sequence. We're going to add them all together. Then, if you look at the second one here, this piece, it says take the sum as k goes from 1 to j. So j is some number in the middle here. And so now we're just going to take the sum from 1 to j. And then that should be equal to the sum of the a sub k's from j plus 1 to n, which is essentially just, the rest of this. Here's j plus 1 here, and it goes up to the rest of this. So what is essentially saying is that you can find this sum here by taking the entire sum and removing this front piece. Let's look at some examples. Example number 9. Rewrite each of the following using one of the properties. So the first one is the sum as k goes from 1 to 7 of 3k. So this would be a constant multiplier here, 3. So we bring the 3 out in front, and we multiply that by k is equal to 1 to 7 of the k. And we won't work this out, but that's just how you would rewrite it using that property, the distributive property. The second one, the sum as k goes from 1 to 100 of k squared minus 4k. So the first thing is I can split it up over subtraction. So we get the sum as k goes from 1 to 100 of k squared minus the sum as k goes from 1 to 100 of 4k. Now, the first one is done. I can't do anything with that. But the second one has a multiplier that I can pull out to the front. But I only pulled it out in front of its sigma, not the entire set of things. Because it's only the second term that's being multiplied by the 4, not the entire thing. Lastly, we have the sum as m goes from 1 to 15 of m squared plus 2m minus the sum as m goes from 1 to 10 of m squared plus 2m. So first off, these two expressions have to be the same for me to be able to manipulate the summations. And then I see what's going on. This first one listed goes from 1 to 15, and then the second one goes from 1 to 10. And we're subtracting it. So we're essentially subtracting off this bit of piece here, and that leaves me with term 11 up through 15. So this is the sum as m goes from 11 to 15 of m squared plus 2m. Notice that the index variable was an m this time. Again, it doesn't matter. A lot of people use k's, a lot of people use i's, but sometimes that gets confusing if you're dealing with imaginary numbers as well. And k's are usual go-to one. Lastly, let's look at summation formulas. So you do need to memorize these. And they are the following. So the sum as k goes from 1 to n of a constant c is just equal to c times n. So what this one is saying is that the sum as k goes from 1 to n of c, the first term is c, the second term is c, the nth term is c. So you have a bunch of c's added together, and there are n of them, so that's just c times n. The second one says the sum as k goes from 1 to n of k is equal to n times n plus 1 over 2. So what you're looking for here is the index variable being raised to the first power. These sequences are basically 1 plus 2 plus 3 plus 4 all the way up to n. And this one is equal to n times n plus 1 over 2. So n is the last term, and then you multiply it by the next number, n plus 1, and divide it by 2. The third one says you're going to take the sum when you square the index variable. So you're going to have like 1 squared plus 2 squared plus 3 squared all the way up to n squared. This is equal to n times n plus 1 times 2n plus 1 divided by 6. So n, the last number, the index that you use, goes here, 1 plus that, and then twice that plus 1 goes there. And then the last one, as long as you got the second one, you got this one as well. So you're looking for cubes. So this will be 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. And that's equal to n times n plus 1 over 2, and you take that quantity squared. So it's just the square of the second one, which is kind of neat. Example 10. Find the sum. The summation as k goes from 1 to 10 of 3k squared minus k. So I'm going to do a little rewriting of this first. So first thing I can do is pull out the 3 from the first term, and we get the sum as k goes from 1 to 10 of k squared minus the sum as k goes from 1 to 10 of k itself. And then, to work this out, I just use my formulas from above. So the first sum is going to be 3 times. Our last number used here is 10. That's the last index. So we're going to use 10 for n. So it'll be 10 times 10 plus 1 times 2 times 10 plus 1 over 6 minus, here we have 10 again, but this time it's the summation of a linear k, so that's just 10 times 10 plus 1 over 2. And then if you work all that out, you get 1100.